Wow. What a turnout. I'm very excited. Good evening. My name is Hirosi Ooguri, and today I would like to raise this question. What is gravity? Well, it may sound like an obvious question to you, that we all think that we know what gravity is. But I'd like to explain that this is not, well, it went out. Maybe you turned off the power for the projector also. I can start talking. Oh, hey, Andy. Maybe you can fix this. He's a professor at Harvard. But this time, he's just doing IT guy. Now he's typing password. Great. So back to the business. So let's see how it works. Oh, yes. So it might sound very familiar. The gravity sounds very familiar to you, but I would like to at least explain to you that it is the most mysterious of all the forces. And it actually holds the key to some of the deepest secret of the universe. So if you get that, then I have accomplished my task. And I would like to do that through 7 wonders of gravity. So I'd like to explain 7 surprising aspects of gravity. The first is the gravity is a force. Well, this is just to set the stage. Well, it might be obvious to you that gravity is a force, but it was not obvious to ancient Greek. For example, Aristotle thought that everything is made on the earth are made of 4 elements, and we are earthy things, and we want to return back to our origin, which is the center of the earth. And so we all have the tendency to go to the center of the earth. And that's how he explained gravity. It wasn't a force to him. It sounds a very funny way of explaining it, but it was sort of economical, because force are the things that works between objects. But gravity works, at least as far as we can feel, only between us and the earth. So it may be more economical to explain that in this way. So to explain why the gravity is force, I have to explain what the force means. And the definition was only given 2,000 years after Aristotle. Newton defined it as something that changed the motion. So for example, if you have gravity, the motion of the ball changes, and that's how you see that there is a force. And by now, after 400 years since Newton, we understand that there are 4 forces in nature: gravitational, electromagnetic, and 2 nuclear forces discovered in 20th century called strong and weak. These are like funny names. Now, we are running out of our imagination, I'm afraid. So strong forces are used to attract quarks to each other, and they make protons and neutrons. And so those are the strong force. And then there is a weak force, which is responsible for radioactivities, why the sun shines, etc. And we understand there are 4 forces of nature, but gravity is the weakest among all the forces. And that's the next wonder. Gravity is a weak, and in fact, the weakest force in nature. And this sounds like a little bit funny to you, because you feel gravity is a force that you feel in everyday life. That's how I'm standing on this podium, for example. But if you think a little bit more, it actually is obvious. But let's take an example here. So suppose I have a magnet here and put some iron on it. Then it stays like that, even though the iron is pulled by the earth downward. But magnetic force keeps the iron here, even though magnet is just a few grams, whereas the Earth is actually a billion times billion times billion grams. So it takes, even if Earth, such a big object, pulls the iron, the magnet wins. This is how weak the gravity is. So suppose I have a cup, or even Andy's laptop here, doesn't fall through the table, even though the gravity is pulling this down. I'm standing on the stage, and even if I do this, I won't fall into the stage. So why is this? The reason is that tables are made of atoms, stages are made of atoms, I'm made of atoms, and atoms are bound together by electromagnetic forces. And since electromagnetic force is much stronger than gravity force, so it resists gravitational force, and that's why I can safely do this. And this is another way to demonstrate that gravity is much weaker than the electromagnetic force. So in fact, it's even weaker than the weak force, so it's the weakest force in nature. Why is this? This is one of the very mysterious things about gravity that is actually we are studying right now. We wanted to explain why gravity is weak, and in fact, the weakest force in nature from some fundamental principle of physics. And the third wonder is that gravity is in the eye of the beholder. So not only gravity is weak, but it's, depending on how you view it, you can make it disappear. So here is an evidence that you can make gravity disappear. So this is a world expert of gravity without gravity. And this photo was taken just a few kilometers above the Earth, where the gravitational force from the Earth is still working. The way this photo is taken was that he was sent by a plane, and the plane went down free fall. And the photo is taken in the free-falling plane. And it looks as though gravity is not working. And this is closely related to what is called Einstein's happiest thought of his life. So 1905, Einstein made 3 important discoveries that changed the course of the physics. One is the discovery of special relativity. And the other is the discovery of the explanation of the Brownian motion, etc. So he actually made 3 important breakthroughs in 1905. But he was working in patent office in Bern. And a couple of years afterwards, he still didn't get a job in the university. And he was sitting on patent office, his patent office, and then thinking about gravity. And then this hit him. And he called this as the happiest thought in his life, that for an observer falling freely from the roof of a house, the gravitational force does not exist. And it took him 10 years after this discovery to formulate it in the law of gravity, which is now called general relativity. And in a nutshell, what general relativity says is that gravity is a warping of space and time. And as I said, it took 10 years for Einstein to turn this happy thought that for an observer falling freely from the roof of a house, the gravitational force does not exist. From this thought, to turn that into general relativity, it took 10 years. So I would like to explain general relativity to you tonight in 5 minutes. Well, I'll try. So here is how I would do it. First, I would like to ask what's space and what is time. And these are like very mysterious things. If you think about space, well, we are supposed to live in 3-dimensional space, and I really see there are 3 dimensions here. But why not in 2 dimensions? Why not in 4 dimensions? Is there something special about 3? The time flow from the past to future, but the way that time flow is very funny. We can remember things in the past, but we cannot remember things in the future. Why not? So there are many things that we don't understand about time. And in fact, if you go back to the history of science, different people have different view of about space and time. For example, it is often said Aristotle abhorred a vacuum. But what it really meant was that he thought that space and time does not exist independently. It exists only when there are stuffs in it. And space and time refer to how this stuff changes. So that's how he thought about space and time. But that view was totally changed by Isaac Newton 2,000 years after that. He postulated that time and space exist independently of physical event, that it exists as some absolute thing, and space and time are absolute. And in it, he formulated a law of physics. So the object, the stuffs are like actors standing on the stage, and stage is like space and time for him. Okay? So that's how he thought about space and time, and that's how physicists thought about space and time for the next 300 years or so. And then Einstein came and totally changed the perspective. So first of all, in the special relativity that he formulated in 1905, he said that space and time actually depend on how you observe them. And in general relativity, he went on further and said that gravity is actually the warping of space and time. So I would like to explain this part now. So here is a caricature of this. There is an Earth, and there is this Earth, and there is the Moon, and they are interacting with each other with gravitationally, and they are bending space and time. So, but in 5 minutes, I cannot explain general relativity in a three-dimensional space. So I would like to simplify things a little bit and assume that we actually live in two-dimensional space. In fact, there is a very interesting novel about that called Flatland from 19th century England. And this is a story of Mr. Square in Flatland. In Flatland, there is a square guy living. And then one day, Mr. Square was taking a walk in London, well, two-dimensional London, and then meet Mr. Sphere. Okay, this is how he meets. So he was walking, and suddenly he sees a point. And the point starts expanding to a circle, and the circle shrink and disappear. What happened? What happened was that he didn't know about it, but there was a third dimension in the universe. And Flatland was just a two-dimensional slice of three-dimensional spaceland. And in the spaceland, there is this Mr. Sphere living. And he visited Flatland like in this picture. And seen from Mr. Square, it looked like there is a point, and the circle expands and shrinks and disappears. Eventually, Mr. Square and Mr. Sphere become friends to each other. Mr. Sphere took him to spaceland and opened the mind of Mr. Square to higher dimensions. That's the story. So on your way back home tonight, if you see a point in front of you, and expand to a sphere, and shrink and disappear, perhaps somebody from 4 dimensions visited you. So anyway, so returning back to the Flatland, so suppose Einstein were in Flatland, how would have he formulated the general relativity? This is how he would have done it. Get a piece of paper. This is your Flatland. Okay? And suppose you put some massive object. This is represented by a red dot. And I want to show you how this red dot changes the space and time. In this case, first, space. So the way that Einstein would have said that was that if you put a red dot there, then you make a cone in this way. You cut an angle from this red dot and glue them together to make a cone. And this is how the gravity acts through this red cone, from this red cone. Red point. So you put some massive object at the red point, and depending on how heavy it is, the angle changes. The heavier the object is, the angle becomes wider, and the cone becomes sharper. And this follows from Einstein's equation in 2 dimensions. So if you write Einstein's equation in 2 space dimensions, the Flatland, then this is what Einstein's equation tells you. And from this, you can see how the gravity works. Because suppose you consider straight object on the Flatland, feeling that there is no gravity in it. But if you put red object in the middle and make a cone, then they meet each other, and the motion of these things are just as if there is a gravitational force between the red object and the blue line. So this is how he would explain the general relativity in Flatland. So this was like 5 minutes presentation of Einstein's general relativity in 2 dimensions. But Einstein's idea is the idea is essentially the same in our 3 dimensions. That we just need a little bit of mass. But there is another feature of general relativity, which is that gravity also warps time. So not only it bends the space, but it also warps the space. So I would like to explain this by taking an example of black hole. And Andy will tell you more about black hole after this. And this is the extreme example of how the time warps in the context of gravity. So black hole is a very mysterious object. It is so heavy, so nothing can come out from it. But suppose one day my wife asked me, well, why don't you go and check out a black hole and see how things are like? And of course, I always say yes to my wife. So I got on a rocket and said goodbye, and then I promised her to send an email every day to report what I see. So I'm going to be on my way to the black hole. And then every day, I send an email to her reporting what is happening. And I keep doing that. And then surrounding the black hole is this very mysterious area called the event horizon that Andy Tramija might tell you about it in his talk. I do not know what he's going to tell you, but this might be something he might tell you. And so anyway, so I pass through it, and then nothing special happens. I keep sending her email every day as I promised. But here she looks unhappy. What happened is that every day she was receiving email from me, but as I approach the black hole, it becomes delayed and delayed. She starts receiving email every other day, every week, once in a month, once in a year, once in 10 years, and then she stopped receiving email from me. And also, when she observed me by telescope near the black hole, it seemed like I got stuck near the event horizon, and just as if I'm hesitate to get into the black hole. Okay? So these are two events. So these look like two different events, but this actually is a description of the same event, seen from different observers, from me on the left and from my wife from the right. These things happen very often, but this is one of those situations. And but it's sort of demonstration of what it means that the warping of time happens in general relativity. So these sound like a very academic and theoretical exercise, but this is actually crucial for us because I believe most of you have a smartphone, and there is a map app in it, like Google Map or something like that. And the way it works is that there are GPS satellites in the sky, and it sends signal to us, and we get that, and we figure out what time it is and where we are. But in order for that to work, GPS satellite must have very precise clock. But the way that clock works is affected by the fact that it's far from above the Earth, and therefore the gravity is weak, and it's also running very fast. So there are very significant special relativity and general relativity effect, which usually combine cause an error of 10 kilometers per day. So if you don't take into account special and general relativity, your iPhone would not work. So this is really significant for everyday life. So I told you that gravity is a force, and it's weak, and it's in the eyes of the beholder, and it's a warping of space and time. And so in particular, I said that gravity is a warping of space and time. Well, the title of my talk was what is gravity? So here's an answer. So I could have sent my talk here, but I'm just halfway through my talk. So the problem is that there is a quantum mechanics in the microscopic world. So in fact, gravity is hard to be unified with quantum mechanics. So just 10 years ago, on July 4th, CERN in Switzerland announced the discovery of Higgs particle. And this was a significant event because it completed the standard model of particle physics. So these are stuffed animal toys of standard model particle. There are 16 of them on the left, and there is one more, that's the Higgs particle, and that's the last piece of the table of elementary particles that makes up standard model of particles. You can buy those things on web. But if you look at this table, the gravity is missing. So if there are forces between gravitational force, there must be a particle called graviton, which has never been discovered. These are only particles that we have discovered so far. So standard model of particle physics does not contain gravity, and there is a reason for this. The gravity is a warping of space and time, but standard model of particle physics described by quantum mechanics. And in quantum mechanics, as you might have heard, the things are uncertain by Heisenberg's principle. That in classical world, if I throw this object over here, I don't do that, but then it takes particular trajectory. But in the quantum world, the trajectory is very uncertain. But on the other hand, I told you that the gravity is a warping of space and time. So if you combine these two, we see that attempt to unify gravity and quantum mechanics would make space and time uncertain. And this is a very confusing thing for physicists. How you come up with a theory in which space and time is uncertain. So this has been a holy grail of modern physics. And there are even movies made of this, actually two. And the only consistent way we know how to combine these two is superstring theory. So that's why some of us are working very seriously about it. Actually, I'm here also for tomorrow and the day after tomorrow. There is a very important symposium honoring the 60th birthday of Erik and Herman Fjarrinde, who is a very distinguished physicist from Holland. And he is an expert on this subject. And I'm very pleased to be here to celebrate their birthday. So superstring theory postulates that fundamental building blocks of the natures are not point particles, but are made of extended objects called strings. And it has helped solve some of the deepest mystery of quantum gravity, such as the origin of Hawking radiation. And again, Andy Strominger might tell you more about it. So for the next two wonders are related, are the kind of wonders that we hope superstring theory would help address. The first wonder is gravity and superstring theory possibly explain why the sky is dark at night. So let me pose the question, well, why is the sky dark is the sky dark at night? Well, you might say it's obvious. That the obvious answer is that, well, the sun is on the other side of the Earth. Well, that certainly is an important element. But there are more to the story. Otherwise, I wouldn't have put it as a sixth wonder. And the reason is that there are also stars. So there are lots of stars in the universe. So if you go certain distance from the Earth, there are a certain number of stars that are shining us and that we can see. Suppose we go twice the distance, then the light, the luminosity from each star would become quarter. Because if you go far away, the light becomes weaker. If you go twice the distance, the light becomes quarter. The strength of the light becomes quarter of that. But if you go twice the distance, there are 4 times as many stars. Because that's if you count the area of the region twice the distance, then there are 4 times stars. So similarly, if you go the 3 times farther, then each star will shine like 1/9 of the strength of the light. But there are 9 times more stars. So the total strength of light coming from all the stars is the same. If you go 10 times the same thing, you get the same amount of light. 100 times, you get the same amount of light, and go on and go on. So that suppose the universe is infinite, and the stars are uniformly distributed. If you add them up, you can deduce that the night sky should be shining at infinite strength, just like the surface of the sun, or even stronger. So this is called Olbers paradox. That was postulated by Mr. Olbers in Germany in 1823. And interestingly, as far as I know, the first person who gave the right answer to the question, why the night sky is dark, was Edgar Allan Poe. You might know his name. He is a famous poet, writer, editor, and novelist. And one of his last books is called Eureka. And this is one of the paragraphs of this book. And in the first part of this paragraph, he explained this Olbers paradox in a very nice way. And then he asked, well, so why there are these dark places in the night sky? Well, the night sky should be occupied by stars. And he explained that the reason is that the distance to this invisible area is so immersed. So there are stars there, but they are so far away that no ray from it has yet been able to reach us at all. So there are stars, but they are very far away, and the light has not got to here. So he, of course, assumes that velocity of light is finite, which is important. But he also assumes that there is a beginning of time. Because if the universe existed from the infinite past, even there are stars that are very far away, there is always enough time for the light to come to the Earth. So in order for this logic to work, the universe must have had a beginning. Okay? And this is exactly what happened. So 80 years after Edgar Allan Poe wrote this passage, Edwin Hubble of Mount Wilson Observatory, this is in Pasadena, it's actually in the same city as I am, and I can see Mount Wilson from my office, which is sort of, I always sort of brag about it. But he discovered that the universe is expanding, and this is how he's showing to Einstein on his discovery. But if the universe is expanding now, if you go back in time, there must have been a hotter and a denser period in the universe. In fact, if you start with the condition that the universe is expanding and going backward in time using Einstein's gravitational equation, then Einstein's gravitational theory predicts that there must have been a big bang at the beginning, which makes the beginning of the universe. You might have seen this. This is the front page of New York Times yesterday. And the NASA's James Webb Telescope unveiled 5 photographs, and Joe Biden, President Biden, actually showed the first of these 5 photos in White House on Monday. And so this is the photo, and some of the galaxies on the photos are like 13 billion light years away. And this is actually as far as you can possibly go, because we now know that the Big Bang was 13.8 billion years ago. And one of the aims of James Webb Telescope is to study those first stars and galaxies that were born immediately after the Big Bang. And these were the first thing. So there were no stars and galaxies before that, and that's why the sky is dark at night. But then this solves the problem, but it raises more problems. So you can then ask what happened before the Big Bang, and if there are something before the Big Bang, how can we observe the universe before the Big Bang? And these are some of the things that superstring theory, we are trying to use superstring theory to address. So anyway, so I wanted to convey to you that such a simple question, like why is the sky dark at night, leads to a very profound answer and leads us to more questions. So on your way back home tonight, if you see the sky is dark, then please remember that this actually is a very profound question. So I would like to end my talk by asking the last question, which is why is gravity just so? So I wanted to explain what I mean by that. So I told you that the universe was born 13.88 billion years ago. This is actually an amazing statement. When I was a grad student, some astronomers said the universe was born 10 billion years ago, and some astronomers said the universe was born 20 billion years ago, and they only knew the number of digits. And then, but now we know the age of the universe in 3 decimal places, so that's really amazing. But another amazing thing is that 13.8 billion years is a pretty long time, as you can imagine. But it's very long for the following reason. So we know that our Earth was born in 4.5 billion years ago, and life emerged like 3.5 billion years ago. But it took 13.8 billion for microbes to evolve to Homo sapiens, intellectual enough to ask what is gravity. So it takes, universe exists a long time, but it also takes a long time for life to emerge and intelligent life to evolve, and evolve into intelligent life. So here is the question. So why the universe is just so? In particular, so for example, why the gravity is weak? This is the second question. So in fact, if gravity was a little bit weaker, then stars and planets would not have formed, because those are formed by having things attracted to each other. But if the gravity was a bit stronger, then most stars we have would have collapsed into black hole, and again, life would not have existed. So the gravity has to be tuned just so in order for the life to exist. And similar, there are other aspects of gravity that seems as if these are fine-tuned to our existence. So this raises a question, why is gravity just so? So one possible explanation being proposed is the anthropic principle, which is to say that gravity is just so because otherwise we would not have existed, and try to answer these questions. Well, this sounds like a silly way to address the issue. And in fact, if you use that technique, then you can answer most of other profound questions. But sometimes it actually is important. And in fact, sometimes it's a true, correct answer. For example, you can ask, how the distance between the sun and the earth determined? So this was mysterious from people in ancient Greek, and people kept asking this question. They tried to explain the distance of sun and planets, like Mercury, Venus, Mars, Earth, and the ratios, from some fundamental principle. I'm told that, for example, Pythagoras tried to explain that using the theory of music, and even Kepler, before he discovered the 3 laws of planetary motion, had some theory to deduce the relative distance of planet to the sun. But we now know that these are not the correct way to try to address the question, because we know that there are many stars in the universe with planets around it, and these planets are at a variety of different distances from their mother star. So that means that the distance from the star to planets are like arbitrary and just determined by historical accident. And the distance from the Earth and sun is just so that the water can stay liquid and life can evolve into intelligent being. And for example, this is the same as trying to see why we are not at the center of the Earth, for example. These are not as habitable places as here, I imagine. So this is a situation where anthropic principle gives the correct answer. So the question is that, is this the same for the explanation of fundamental laws of nature, such as why the gravity is weak? So this is actually now scientific question, because superstring theory, in principle, can come up with a variety of different laws of nature, and then you can consider applying anthropic principle, and this is something that people are hotly debating these days. So I'm running out of time, so I should stop here. So I presented 7 wonders of gravity. The gravity is a force. It's weak, as in the eye of the beholder, and it's warping of space and time. And that would have been the end of my talk. But since we have quantum mechanics, the story continues. And then there are lots of interesting questions, like what happens at and before the Big Bang, and why gravity tuned just so. And there are also many questions about black hole that perhaps Andy Strominger will tell you about. Thank you very much for your attention.